Hello friends! Here is a video of conservation of momentum, a physics topic that seems a bit complicated but it's quite easy. Let's move on to it. Good morning friends! I'm Mahima and here I'm there to teach conservation of momentum in a very easy way. So friends, let's go to our topic. So before we enter into conservation of momentum, it's important to recall Newton's third law of motion. We will see that it's very important in this topic. So let's recall it. As we know, Newton's third law of motion says every action has equal and opposite reaction. What does this mean? Here I've taken an example of a carom board. Here two objects are striker and the wall. So say I hit the striker with 50 newtons. What does it happen? It comes back with the same magnitude, 15 newtons. But what might be the direction? Of course, opposite. Thereby, according to Newton's third law, it says force of object A on object B. Here, force of striker on the wall is equal to minus force of B on A. That means minus force of wall on the striker. That is 50 newtons equals minus 50 newtons. We got to know every action has equal magnitude now. Equal magnitude, action and reaction has equal magnitude. That is 50 newtons equals minus 50 newtons. But here, why are we mentioning minus? Minus is denoted here to say that it's in the opposite direction. Thereby, we get every action has equal reaction, that is equal magnitude, and opposite reaction because it comes in the opposite direction. So now, as we have recalled Newton's third law of motion, let's move into our topic, conservation of momentum. So here, let's see the title, conservation of momentum. What are the keywords you can see here, friends? Of course, there are two. Conservation of what? Of momentum. What is momentum? Momentum is defined as mass into velocity of an object. And how are we conserving this momentum now? Let's see the definition that is given. Sum of the momenta is the plural form of momentum, of the two objects before collision is equal to that of after collision. So according to this definition, we get to know that mass into the velocity, because momentum is mass into velocity. So mass into velocity of the two objects, when we sum it before collision, that value will be equal to the mass into velocity of the two objects after collision. Will this happen every time, friends? We will see that. Now let's see first how is this conservation of momentum equation derived from. It's derived from Newton's third law of motion. That is why I said it's important to recall Newton's third law. So let's see. Force of A on B equals minus force of B on A. So here, this is Newton's third law that every action has equal and opposite reaction. Force can be split as mass into acceleration. We know this because force is ma, that is mass into acceleration. So mass of object A into acceleration formula is v minus u by t equals minus of mass of object B into v minus u by t. Thereby, when we substitute it with basic mathematics, you can refer here what I've given, but I'm telling just the last equation. The last equation we derive after transposing and doing basic mathematics, we get mass into initial velocity of object A plus mass into initial velocity of object B equals mass into final velocity of object A plus mass into final velocity of object B. So friends, what can we infer from this? Of course, we get to know that the momentum of the objects, because mass into velocity is nothing but momentum, and momentum's plural form is momenta. So momenta of this two objects when we sum it before collision will be equal to the momenta of the two objects after collision. Thereby, LHS side it is initial momenta. We have taken initial velocity, and RHS side we have taken final momenta, that is final velocity we have taken while calculating. Thereby, we get to know from this equation that initial momenta is equal to final momenta. And also friends, down I have written in quotes, no external force. What does this mean? No external force is the condition given for this definition of conservation of momentum. Conservation of momentum is applicable in all cases except one case, that is, no external force should act on it. We will see how this works in our daily life with a simple example, very simple. Let's see what that example is. Of course, it's a carom board. So friends, while playing a carom board, have you ever observed the physics behind it? Let's see what it is. For clear reference, I've given again m is mass, u is initial velocity, v is final velocity. And I've taken two objects, striker and the pawn. So according to physics, what can we observe here? We can observe three things: mass, initial velocity, final velocity. Let's find out these two objects, mass, initial velocity and final velocity. So striker, for example, mass I've taken 3 grams. It could be anything. For example, I've taken 3 grams, and pawn's mass I've taken 2 grams because it's a bit lighter than striker. And in my example now, it is like I've hit the striker, but still it is not collided with the pawn. Thereby we can say the striker is in motion. So I've taken initial velocity as 4 meter per second. It cannot be 0 because it's not rest in my example. It's in motion. And final velocity, what could be of striker? It should be 0. Why? Because when we hit the striker, it touches the pawn. And what happens to the striker? It initially comes to rest, whereas the pawn starts moving. So these two are vice versa. Striker, first it's in motion, so its initial velocity is 4 meter per second, and final velocity is 0 because it comes to rest. And the pawn is initially at rest, so the initial velocity is 0 meter per second, and final velocity, you can see I put question mark. You can think why. Because we are going to solve this as a problem for conservation of momentum, so that even we learn how to solve numericals. But here we can guess what can be the final velocity. What could it be, friends? Of course, it could be something more than 0 because it's in motion now. The final velocity will be something more than 0 meter per second. So let's see. Here I've given a summary of what we have learned till here. We can see it clearly, friends. Mass of two objects, A and B, 3 grams, 2 grams. Initial velocity and final velocity of both the objects can be clearly viewed. And then down, I've written initial momentum. Now in my example, what is the initial momentum? We learnt it in the second slide. So mass into initial velocity of object A plus mass into initial velocity of object B. That is before collision, momenta of the objects before collision. And final momentum, mass into final velocity of object A plus mass into final velocity of object B. That is after collision, the momenta of the two objects after collision. Thereby, we got in the second slide itself that conservation of momentum is initial momentum equals final momentum. Let's see if this is proved in our example. The example which we have taken as a carom board with all the values. So here friends, above you can see highlighted momentum equals mass into velocity. Momentum is denoted by P. So P equals mv. And here I've solved the problem. That is, I've found out the velocity of B, which we had kept question mark. We can solve this by using conservation of momentum equation. Mass into initial velocity of object A plus mass into initial velocity of object B equals minus of mass into final velocity of object A plus mass of B into final velocity of object B. Thereby we know that every action has equal and opposite reaction, Newton's third law. That's what I've written in the first line. Force of A on B equals minus force of B on A. When we split this only, we got the equation conservation of momentum. For that recalling purpose, I've given that. So here, mass of object A, 3 grams into initial velocity of object A, 4 meter per second, plus mass of object B, 2 grams into initial velocity of object B, 0 meter per second, equals minus of mass of object A, 3 into final velocity of object A, 0 plus mass of object B, 2 grams into final velocity of object B we have to find. So I've kept it as VB, final velocity of object B. Thereby when we substitute the values, 4 3s are 12 plus 2 zeros are 0 equals minus of 3 zeros are 0 plus 2 VB. When we substitute it again, 12 equals minus 2 VB. So we get Vb equals minus 12 by 2, that is Vb equals minus 6. Thereby we found out velocity of object P equals minus 6 meter per second. But friends, how can we verify this? If you get that question, then let's see how can we verify this. That yes, initial momentum is equal to final momentum. So in this example, our initial momentum and the final momentum should be 12 equals 12. Let's see if that happens. How can we do that? We can do that by putting this minus 6 value instead of Vb in the equation. Thereby we get 3 into 4 plus 2 into 0, same thing, equals minus of 3 into 0 plus 2 into minus 6. So in the next line we get 12 plus 0 equals minus of 0 plus 2 into minus 6. We get 12 equals minus of 2 into minus 6 is minus 12. Minus into minus cancels and 12 equals 12. So we got to know that initial momentum is equal to final momentum. Thereby, it is proved that yeah, actually this happens in our daily life. The momentum is conserved every time. Now we get to know the meaning of conservation. Why is it said that that momentum is conserved all the time? Because see friends, in both the sides, both the objects have different velocities and different masses. Different velocities means different initial and final velocity and different masses. But still, when we sum it together, that is, LHS side we sum the mass and initial velocities of both the objects, and RHS side we sum the mass and final velocities of both the objects. But still, how much ever they differ with the values, at last we get same values on both the sides. That proves that conservation of momentum works in all cases. But I had said you that one case is there for exception for this, that is no external force acting on it. So here what could be the external force acting, friends? It could be frictional force. I think that you all remember what is frictional force. Frictional force is the force acting in the opposite direction. So here, think practically, friends. When you're playing carom, if you have not powdered the board, then there are chances that with the force that you hit the striker may not reach the pawn. It may stop in between. Why does this happen? Because there is a frictional force that board is giving out on the striker. Thereby, the frictional force could stop the striker. That time we cannot say that force of A on B is equal to minus force of B on A. It will not be equal, and also conservation of momentum. That is, sum of the momenta before collision will not be equal to sum of the momenta after collision. That is why the definition of conservation of momentum altogether could be said like sum of the momenta of the two objects before collision is equal to the sum of the momenta of the objects after collision until there is no external force acting on it. Thereby, friends, I would like to conclude by just summarizing what I have just said from the beginning. First of all, we recall Newton's third law of motion. Every action has equal and opposite reaction. And secondly, we saw what is momentum. Momentum is defined as any object's mass into velocity. Plural form of momentum is momenta. And we at last saw what is conservation of momentum. We learned the definition, we learned the derivation, we saw an example, and also we solved a problem. Isn't it easy, friends? So friends, hope this has been a helpful one for you. Thank you.